Welcome to Investigation 3.3, and in this one we were planning for a field trip. If you remember, we underwent a field trip to a science center where we essentially needed to figure out what the average cost was going to be, depending on how many students were going to be there. We had a fixed amount of $750, and if 10 kids showed up, they would have to split a cost of $75 a piece to be able to pay for the trip. Or if 100 students came, it would only be $7.50. So essentially through this, we were finding individual cost. So our focus question for this particular investigation was, how does the cost per person change if a fixed total cost is split among an increasing number of individual players? I also gave the example of if we had a pizza party in the classroom and 2 people showed up, if the pizza cost me $100, those 2 people would be paying me back $50 a piece. However, if we had 20 people show up, everybody would be paying a very reasonable $5 per piece for the pizza party. So in that case, we are also seeing everything, as the number of people increase, we're seeing a decrease in price, which is what we would anticipate. So let's see exactly how that's decreasing. Is it going to be a linear decrease or is it an inverse decrease? So here we go. We have a little problem here. The route for a one-day charity bike ride covers 50 miles. Individual participants ride this distance at different average speeds, as shown in the table below. And so we have this table where the speed is slowly increasing by 4 miles per hour, and the time is decreasing. So if we look at it for 4 miles per hour, the time that would take somebody would be 12 and a half hours. If they rode, though, at 20 miles per hour, it'd only take them 2.5 hours. So we need to write an equation for this relationship. So let's think about it. We have 50 miles to travel. Our speed is the thing that's really changing. So 4 miles per hour or 8 and so on. And then we come up with a time. So if we were relating that 50 miles divided by the speed, we would get our average time that it would take. So 50 divided by the speed of 4 will give us 12.5. 50 divided by 20 gives us 2.5. Excuse me. So that is our equation that we're going to use. So using that equation, let's go on to the next part of the problem. Tell how the riding time changes as the average speed increases from 4 to 8 miles per hour, from 8 to 12 miles per hour, and from 12 to 16 miles per hour. So let's start with that first set of data. We had 4 miles per hour, and that is changing up to 8 miles per hour. So let's get some of the related data for that situation. So for 4, we are at 12.5 for the 12.5 hours, and for 8 we are at 6.25 hours. So what I'm seeing here, if we are talking linear sort of situations, if this was linear, if this increased by 4, I would want to see a constant increase here, or decrease or increase there. So I see a decrease of 6.25 hours. So now let's look at the next set of data. If we look from 8 to 12 miles per hour, we have that same 4 increase in miles per hour. So we have that constant increase. So if this were going to be linear, I would want to see this 6.25 hours become 0. So let's see if that is actually the case. Because if we're looking at a linear relationship, that's what should happen. So we have 6.25. We know that's how long it takes at 8 miles per hour. If it was linear, we would anticipate this. We could predict that as being 0 hours. But if we remember from our table, 12 didn't get us 0. 12 gives us 4.17. So let's add that to our information here. We have actually 4.17 hours. So that's not the decrease that we were anticipating. Instead of this 0 mile per hour prediction, it was incredibly off. And instead, we have a decrease of 2.08 hours. That is not at all what we anticipated. As well, let's look at 12 to 16 hours because that's our last jump. So if we have 12 miles per hour to 16 miles per hour, how does this change? And again, if it was the same as the initial one, this is an addition of 4 miles per hour, we would expect this 4.17 to be negative if we were subtracting 6.25 from it. However, if we're going to subtract 2.08, maybe it's linear now, then we could maybe see around 2 hours for 16 miles per hour. So let's see if that's the case. At 16 miles per hour, it's not 2 hours, it's 3.125. 3.125. So essentially, we have a decrease of less than 1. So less than 1 is our decrease now. We have, actually, no, it's a little more than 1. Sorry. It's about 1.05 is our decrease. 1.045 is our decrease this time. Not at all consistent. So our last question here is this. Do the answers above show that the relationship between the average speed and time is not linear? And like we said before, when we're looking for linear situations, we're looking for a constant change in one variable versus a constant change in the other variable. And in this case, I'm not seeing a constant change between our miles per hour. Well, actually, I am seeing a constant change in our miles per hour, but I'm not seeing that reflected in our hours in comparison. So the answers are not showing a linear relationship. So that is my final answer. So that's something that you can pay attention to when you're looking for inverse relationships. If you're seeing if you can create a consistent change in one, so essentially going up by 2, going up by 1, going up by 4, whatever it may be, maybe going up by 1,000. But if you're not seeing that consistent change in the y-axis, it could be that you have a linear relation or an inverse relationship. We know for sure it is not a linear relationship. If it's inverse, however, we are going to see an interesting decrease, and we will talk about that during class. Thank you so much for listening. I hope you enjoy your homework, and if you have any questions, as always, please ask in class. Thank you, and ciao.